And thank you everyone so much for having me and listening to my talk. I'm a final year doctoral candidate at the EMIT Interdisciplinary Program in Environment and Resources, also known as EIPER at Stanford University. I study electrification policies in the global south. Today, I will be sharing results from a project where I look at the impact of a change in India's rural electrification program on its agriculture. I will begin with some background on how we currently think about electrification and what motivated this research and the specific research question. Next, I will go on to the empirical approach I use and then present a few results. I will end with a discussion on the possible threats to identification and how I address them. Electrification is most commonly measured as an indicator of whether a household has an electricity connection. This graph illustrates the proportion of a country's population that is able to access electricity going from red to dark green. The countries that have been grayed out are ones with universal electricity access. Latest data from 2018 indicates that about 800 million people across the world still lack access to electricity. Electricity access is primarily a rural challenge across the developing world owing to the high cost of connecting far-flung places with the central electric grid. As a consequence, a large chunk of the progress made in electrification has stemmed from off-grid solutions, such as solar lanterns and microgrids in the last 2 decades. This tremendous progress has been fueled by vast sums of financing from governments and aid agencies. The World Bank alone spent over $5 billion across 35 countries between 2010 and 2015. And yet, most of the research studying the impacts of electrification finds little evidence to suggest that when households receive electricity connection, it leads to increases in their income, expenditure, or employment in the near or long term. But we do know that electricity fuels multiple industries and is essential to economic growth. So maybe the question we should be asking is not, does electricity impact household income, but how and when does electricity impact income? The difference between the two questions is that in asking how, we're studying the mechanistic pathway through which people are able to convert the electrons that they receive into avenues of earning money. In my research, I look at how electricity translates to increases in household incomes. And to answer this question, I looked at India, which has made rapid progress in electrification in the last 2 decades, and yet houses the third largest population without. These applications often occur outside of homes, seen here by a woman operating an electric oil press in the top left corner, a hair salon using electric razor next to it, a man pumping groundwater using an electric pump set, and a vegetable vendor using light to sell produce by night. On the other hand, consumptive users of electricity improve quality of life and occur mostly inside homes. Other than the location of where electricity is used, productive and consumptive users of electricity also differ greatly on the power required to operate them. On the left are some commonly used domestic appliances and their power requirements. Together, all of them require about 2/3 of power capacity of the as compared to the smallest electric pump set available in the market. So throughout my talk, I will be talking about productive uses which require much more electric power to operate them and often need to be used outside of homes. Coming back to India. In India, electricity plays a crucial role in the rural economy through groundwater pumping. Over 60% of all irrigated land is irrigated using groundwater. Water from 70% of these groundwater wells is pumped using electricity, and together, these electric pumps consume about 166 billion units of electricity, which is over a fifth of all electricity sales in India per year. And they extract nearly 250 kilometer cubes of water, which is more than the annual consumption of US and China combined. At the agrarian household end, groundwater irrigation helps increase agrarian household income through three main ways. It helps increase the number of cultivation cycles in a year by allowing production during dry months. It helps increases returns to investments on land, labor, and productivity. And it helps farmers diversify cultivation to high value crops which require more frequent and predictable irrigation. However, there is a distinct spatial pattern to the use of electricity in agriculture. In this figure, the intensity of green color indicates the units of electricity consumed by agriculture normalized by cultivated area in the state. And the size of the red dots illustrates the number of groundwater wells with electric pumps per 1,000 hectares of cultivated area in the state. So both the number of wells with electric pumps and the units of electricity consumed are much lower in the eastern region of the country as compared to the northwestern and the southern regions of India. This got me thinking about the reasons behind this observed spatial pattern. To understand the spatial pattern, I dove into the evolution of rural electrification policy in India. In India, electrification in many rural areas accompanied the Green Revolution during 70s to aid irrigation. The targets of rural electrification policies were the number of wells that were electrified and the irrigated acreage. By the early 90s, India had gained self sufficiency in grain production and, in fact, had become a large exporter of rice and wheat, which it continues to be today. Meanwhile, the Central Planning Commission of the country also started expressing concern over groundwater depletion, which was witnessed in some parts of India. So, the cumulative impact was that rural electrification was reconfigured towards village and household electrification. So the number of villages and households electrified became the new targets of the reconfigured rural electrification policy. While on the national level, the country is no longer concerned about self sufficiency in grain production, the situation is starkly different at the household level. Even today, nearly 40% of India's total population relies on agriculture for its income, and the proportion is much higher when you look at just the rural poor. Alternatives to agriculture for employment in rural India are almost non existent, and which is why increasing farmer income remains an important lever for addressing rural poverty. So, the question that I ask is what impact did this change in India's rural electrification policy have on the expansion of its groundwater irrigation? So, using three sources of data, I constructed a novel panel data set of districts in India from 1986 to 2013. The three sources are minor irrigation census, which provides data on how many wells per district, how much area each well irrigates, the depth of wells, the energy used for pumping water from the well, so on and so forth. Household census provides data on the number of rural households as well as households with electric connection. And rainfall data here are used to control for the persistent differences in rainfall that may exist between districts. Using the constructed data set, what I measure is whether there is a difference in the growth of groundwater irrigation between districts that electrified late after the policy change and districts that electrified early for comparable changes in household electrification. Late electrifiers here refers to districts that electrified after the policy focus shifted towards household electrification. So districts that aren't late electrifiers are ones that got electrified before the change when policy focused on groundwater irrigation. The reason I include household electrification is to compare districts which have the presence of electricity grids. I here refers to the unit of observation, which is district, and T is the year of observation. Because India is such a large and heterogeneous country, I include district fixed effects. I also include region specific time trends, which accounts for changes that may have been occurring over the nearly 30-year period that my data spans. The parameter of interest here is beta. If my hypothesis is correct and the change in policy led to less robust growth in groundwater irrigation, beta should be negative. In this coefficient plot, the solid line represents the overall effect of electrification on groundwater irrigation, and the dotted line represents beta, the added effect of being a late electrifying district. I find that overall, with increasing household electrification, groundwater wells with electric pumps increased. But as hypothesized, beta is negative and significantly different from zero. So the cumulative effect of electrification in the late electrifying district is much less than early electrifying ones. Now, turning to groundwater wells with diesel pump sets. Diesel is the alternative energy source for pumping water, but it is much more expensive to operate diesel pumps as compared to electric pumps, which is why it makes sense that we see that with increasing household electrification, there is a decrease in the number of wells using diesel pumps. Here, the opposite trend is true. Beta is positive and significantly different from zero, implying that late electrifying districts actually reduced fewer number of wells with diesel pumps, which makes sense since farmers did not have the option of substituting wells with diesel pump sets with electric ones. The estimate size associated with the loss is large and indicates a loss of over 30,000 wells with electric pumps on average in late electrified districts due to the policy change. In 2013, which is the last year of my data, the average number of wells with electric pumps in late electrified districts was similar, implying nearly a 50% decrease. Next, I looked at the average area irrigated during dry season and monsoons. Monsoons are when the country receives rainfall and like concentrated in bulk amount across a few months. Again, the overall effect of electrification on irrigated area is positive in both seasons, but the difference between late electrifying districts and the overall effect is negative and statistically different from zero only in case of dry season, which makes sense because groundwater irrigation actually becomes much more important during dry season when surface flow and rainfall is reduced. The effect size here too is large and amounts to an average loss of 30% irrigated area attributable to the shift in policy from groundwater irrigation to household electrification. What is interesting is that when I controlled for wells with electric pumps in my regression on irrigated area, the negative effect of beta persists in the dry season, which means that wells with electric pumps play only a partial mediating effect in the relationship. The two possible explanations come to mind. First, there could be differences in electricity supply among late and early electrifying districts. And second, the pump size in late electrifying districts could also be smaller, possibly due to a difference in the transformer capacity and other electricity infrastructure erected in districts electrified under the new policy. Unfortunately, I could not directly test these since there isn't data on electricity supply or infrastructure at the district level. It could be that there is selection bias due to systematic differences between early and late electrifying districts, which made one set electrify early. I find that the two did not differ in the need for irrigation, as seen here in the table. While the overall working population in agriculture was larger in late electrifying district, the population of cultivators, who are the ones who actually make the decision on irrigation, was not statistically different. And neither was rainfall received during the dry, this is during the dry season, Rabi. Next, I looked at the distributional effects in groundwater irrigation. It could be that there is concentration of poorer farming households in late electrified districts, which explains why there is lesser growth in groundwater irrigation. This reason may especially be valid because the new rural electrification policy removed connection costs for household electricity connections, but not well connections for poor households. So using survey data from a single year in 2013, I constructed household consumption quantiles for households in both early and late electrified districts. The unit of observation here is a household denoted by H in district I. And so now I'm comparing the area irrigated by a household in the lowest consumption quantile in late electrified district with a household in the lowest consumption quantile in the early electrified district. As before, the dotted lines here represent the late electrified districts, but now the solid lines represent early electrified districts. So going from top to bottom, consumption increases or the households become richer, and we are comparing the average area irrigated with the poorest household in the early electrified district. So first, comparing households of similar wealth between early and late electrified districts, I find that the difference persists in average area irrigated during dry season. What is particularly astonishing is that the negative effect persists even amongst wealthiest households. That is, on average, the wealthiest household in the late electrified um, district irrigated less than the poorest household in the early electrified district. Again, these differences diminish for monsoon or wet season irrigation. So what I'm not able to control for are the size and the fragmentation of land holdings. It could be that farmers with smaller plots but similar consumption may be disincentivized to buy electric pumps, particularly if they have the land distributed across multiple parcels. I can't account for pre-trends, which is why I'm unable to carry out a difference in difference analysis. And finally, I alluded to the possibility that electricity supply may be playing a role, but I'm unable to test it directly. So, in conclusion, my results suggest that a change in the rural electrification policy in India did limit the expansion of groundwater irrigation among districts that electrified under the new program. My field visits in a few states suggest that placement of wires and poles and the size of transformers could be the reasons behind why farmers are unable to access electricity for groundwater irrigation pumping in newly electrified districts. Reduction in dry season irrigation among new electrified districts implies negative outcomes for food security and farm incomes in these regions. I only looked at groundwater pumping, but it could be that the transformer size and placement of poles and wires could also be constraining other productive uses of electricity. And so, more broadly, we may need to rethink our target of domestic electrification and whether that might be limiting income enhancing or productive uses across the developing world, explaining the null effects of electrification on household incomes that we find in literature so far. And with that, I'll end. Thank you.